Hi everyone, this is Jin from Alibaba Cloud. Today I'm glad to introduce you to Lindum, the serverless compute engine on multimodel architectures. In this talk, I will first give you a quick overview of what Lindum is and why it matters. Then I will walk you through its core architecture, highlighting how it combines serverless computing with multimodal data and deliver simplicity, scalability, and high performance. Let's get started. Driven by AI and new energy, data is undergoing a profound transformation from structured data in the PC era to semi-structured data in the internet age. We now live in an AI era where large models unlock semantic understanding of unstructured data. Text, images, audio. Modern applications must process its multimodal information. Queries have evolved from simple keyword matching to semantic search and real-time responses. To meet these demands, traditional architectures often combine multiple systems, like MySQL, Elasticsearch, ClickHouse, Redis, thus creating a fragmented stack. Scalable but brings key challenges. Low building efficiency due to inconsistent APIs and metadata. High operational complexity from managing multiple pipelines and rising costs caused by data redundancy and inefficient resource use. The larger the system, the greater the burden. The future lies in unified data system. These unified structured and unstructured data under a single architecture, combining vector, full text, and graph engines for semantic understanding and instant querying. Automated indexing and elastic scaling reduce redundancy and cost. A unified system smooths development, simplifies operations, and maximizes data value. I would like to introduce Lindum, a cloud-native multimodal data platform built for the AI, not just a database, but an integrated system unifying storage, computing, search, and AI inference. As AI applications grow, data comes in diverse forms and massive volumes with rapidly changing needs. Traditional architectures stack systems like HBase, Elasticsearch, and Spark, leading to high costs and low efficiency. Can one system handle it with one deployment? Lindum answers yes. Lindum has a five-layer architecture. First, flexible cloud native storage resource layer. Second, LDFS, our self-built file system, providing stable, low-cost storage. Third, file multimodal engines. Messaging, whitetable, search, columnar, and vector cover all data scenarios with open source compatibility. Fourth is a computing engine, supporting batch and stream processing. It includes LDAI, an in-database AI inference engine powered by NVIDIA Triton and TensorRT. Fifth, unified interfaces. LSQL support seamless integration. Lindum provides core capabilities. First, fused search, real-time synchronization of text, vector, and scalable indexes for millisecond retrieval. Second, in-database AI inference, models as database functions, enabling vectorization and ranking via SQL. Third, elastic scaling, storage, compute, and AI resources scale independently to handle traffic specs. With open source compatibility and unified operations, Lindum cuts migration and development costs. It's not just a database, it's an AI-era data foundation, empowering developers to focus on innovation. Next, I would like to introduce Lindum's super wide table, a truly distributed data model for the AI era, designed for massive scale, extreme flexibility, and rich multimodal expressiveness. First, it handles enormous scale. In use cases like connected vehicles, user profiling, or AI feature storage, data can reach tens or hundreds of terabytes. The superwide table supports single table capacity up to petabytes, with infinite horizontal scalability. Second, it offers exceptional flexibility with thousands of dynamic columns, Unlike traditional databases with rigid schemas and costly migrations, Lindum allows on-the-fly column addition and deletion. Columns can scale to tens of thousands, and new user tags or sensor data take effect instantly. Each column updates independently, combining agility with strong consistency. Most importantly, it supports rich data types: strings, numbers, blobs, vectors, JSON, and arrays, all in one table. Next, let me introduce the Lindum computing engine, which is a core serverless component in Lindum architecture. With AI's rise, processing unstructured data efficiently requires seamless orchestration of heterogeneous CPU and GPU resources. A key challenge: GPU-intensive tasks must work in sync with CPU-based I/O and control logic. Traditional frameworks like Spark use staged execution, causing blocking and idle periods. This hurts efficiency. Lindum solves this by integrating the open-source Ray framework, which uses a streaming execution model. Multiple operators run in parallel as a pipeline, keeping both CPU and GPU continuously busy, eliminating idle time and maximizing utilization. Also, Ray's native Python support makes it ideal for AI and unstructured data. Architecturally, Lindum deploys Ray in a serverless way, enabling elastic scaling. Hybrid resources are allocated on demand when a job starts and released after. Beyond elastic ETL and Ray, Lindum offers a dedicated analytic engine with MPP architecture, which delivers over 8 times faster queries than open-source Presto, ideal for interactive analysis. In summary, Lindum's computing engine unifies serverless elasticity, AI-powered ETL, and high-speed analytics, providing a flexible, efficient platform for the AI era's complex data demands. In the next section, I will introduce some core technologies in Lindum. We say Lindum provides user a logical wide table with multiple engines supported. With a unified logical view, you can perform traditional operations like point queries and analytical processing. At the same time, you can handle modern AI-driven tasks such as full text search, vector similarity search, and semantic retrieval, all within the same system. This is made possible by our unified SQL interface, which supports schema evolution and zero-etl. No more complex pipelines or separate systems for different data types, whether it's structured data or unstructured data, or text, vectors, JSON, or arrays. Everything flows into one logical table and is automatically indexed across multiple engines. Wide table engine for the faster key lookups, search engine for text retrieval, vector engine for high-speed similarity matching, and columnar engine for efficient analytics. We see Lindum a truly mixed workload platform that reduces data complexity and simplifies development. Developers no longer need to manage multiple APIs, coordinate ETL jobs, or maintain inconsistent metadata. Instead, they can write a single SQL query to combine filtering, searching, and vector matching. Next, I will introduce the core capabilities of Lindum in real-time data synchronization and analysis. In traditional data analysis architectures, data is typically synchronized from TP system to AP systems, or data lakes where ETL. However, this multi-link architecture comes with high data latency, complex maintenance, and high costs. To address these issues, Lindum introduces the concept of lakehouse real-time integration. As illustrated, users can read-write data through a wide table serving. When business requires higher analytical performance, columnar indexes can be created on demand. Similar to secondary indexes in MySQL, the underlying columnar data is managed by Lindum's columnar engine, utilizing an efficient columnar storage format that supports automatic tiered storage. On the query execution level, the SQL engine selects the execution path based on query complexity. The simple queries are processed locally, while complex queries are forwarded to Lindum's computing engine for distributed computation. This system provides robust operational capabilities utilizing a producer-consumer model. It achieves high throughput with isolation mechanisms, ensuring real-time synchronization priorities. Now, let me introduce the core technical architecture of Lindum in high-performance real-time data warehousing scenarios. Firstly, consider the three pivotal stages in data analysis: data ingestion, ETL processing, and query analytics. Achieving high performance and real-time capabilities across three stages is crucial for building a modern OLAP systems. During the data ingestion phase, batch loading serves as a foundational capability. The true challenge lies in real-time writing, updating, and deletion. To address this, we have built a hybrid row-columnar engine. This allows for real-time data ingestion, while leveraging the hybrid structure to efficiently support scanning, filtering, point queries, range queries, and serving scenarios, accommodating multiple types of workloads. In the querying stage, beyond compression encoding, code pruning, and clustering and sorting at the storage layer, vectorized execution engines and optimizers play vital roles. Our vectorized engine deeply optimizes operators such as sort, scan, and join, fully utilizing CPU superscalar pipelines, prefetching, and SIMD instruction sets to achieve maximum performance with minimal resources. On the optimizer side, we support runtime filter for dynamic join filtering, trimming large amounts of data before network transformation. Combined with dictionary encoding as a storage layer, it accelerates operators like scan, filter, and aggregation. For ETL processing, traditional models rely on T+1 batch scheduling, limited by query and write performance. Innovatively, we introduced real-time incremental materialized views that enable automatic incremental refresh, driven by data changes. This not only maximizes hardware resource utilization and reduces overall computation, but also boosts query speeds. In conclusion, Lindum provides a high-performance real-time data warehouse through vectorized execution, intelligent optimizers, and unified batch stream ETL processing. Finally, I will post a use case helping you better understand Lindum. In autonomous driving and connected vehicles, we face massive challenges. Thousands of raw data records are uploaded every day. Data computing efficiency is a key challenge. Our user built an integrated data loop on top of Lindum. Vehicle data is ingested in real time via Lindum streaming using CEP and UDFs for stream processing. It then lands in Lindum's multimodel engine, supporting row, inverted, and columnar storage, enabling high-performance computing across data types. AI nodes powered by the Ray framework automate rule-based tagging, generating labels, then produces training-ready datasets. Finally, data is output, optimized for downstream training platforms, greatly improving access speed. Lindum's white table handles millions of QPS, managing trillions of tags, dramatically simplifying infrastructure and boosting development efficiency. We also explore dynamic file formats to enhance integration between data and training platforms. We can see Lindum unifies storage, real-time computing, AI inference, and analytics. It supports efficient processing for both batch and streaming workloads. This architecture delivers simplicity, low cost, high performance, and elastic scalability, a true one-stop solution for dynamic AI data. That's all my talk. Thank you.